everybody, this is Suvarchala, working as an associate professor, Institute of Aeronautical Engineering. In this video, I'd like to discuss how the logs are going to be implemented by the concurrency control manager and how these logs are implemented if the data will be considered in granularity, multiple granularity. So we discussed in previous video various techniques for executing the transactions concurrently. As a part of that, we already discussed two-phase locking protocol as well as deadlock handling. In two-phase locking protocol, locks are going to be requested by the transactions and are allocated to serve these transactions by using various techniques by the concurrency control manager. And also, we discussed two kinds of locks are going to be considered: exclusive locks and shared locks. And the compatibility matrix was also discussed, based upon which the locks are going to be allocated to the transactions in concurrency control environment. Now, how this allocation of the logs or releasing of the logs, etc., are going to be managed. To manage all these logs, a log manager component will be there. A log manager can be implemented as a separate process which transactions send logs and unlock request. Whenever a transaction sends a log request or unlock request, that will be carried out by this a special component known as log manager component. This component will manage the logs on data items, whether the data item is free or not. If the data item is already logged by some transaction, what type of log is there, and whether this requested transaction can be served immediately or the transaction will be made into waiting state. All these things are going to be manageable by this logging manager. The log manager will implement all the issues related to the logs action. This log manager replies to a log request by sending a log grant message. A message will be sent, your log is granted, so that the transaction can continue further. Or if it is not free, that variable is not free, a message is asking the transaction to wait. Or it may request a message to roll back if it is in deadlock state. All these are going to be taken care by this log manager. Because log manager will decide which transaction is waiting for which log and which was held by which transaction, all these details are manageable by this log manager. The requesting transaction waits until the request is going to be answered or served by the log manager. To implement these logs, log manager maintains a data structure called a log table. Because it has to keep track of all data item status as well as the transaction request status. No? So that's why it will maintain a log table to record granted logs and pending requests. The log table is usually implemented as a in-memory hash table. In-memory means RAM. Currently, which of the transactions are going on, only for that only the log requests are going to be requested. No? So that's why in-memory hash table is going to be used or generated and maintained by this log manager. Once the system is going to be switched off, no transactions will be there. No? Then automatically no need to maintain the table request. So that's why log manager maintains this log table as an in-memory hash table indexed on the name of the data item being logged. Indexing variable will be data item actually. And I'll show you next slide a diagram in which dark blue rectangles indicate granted logs, light blue rectangle indicates waiting request. And log table is also records the type of the log granted or requested, both type also, exclusive or shared. Any new request is added to the end of the queue of request of the respective data item. So for each data item, any request is there, that request is going to be added, keeping on adding which transactions are waiting in for that particular data item in queue. And also once the granted, if it is compatible with all earlier locks. Once the lock is going to be released, the respective item is going to be our request as well as served. Both are going to be released or deleted in our lock table also. So this is the lock table. Please observe. In this lock table, I7, transaction I7 is there. So transaction T23 is requesting for I7, and then lock I23. This is requested by two T1 transaction, T8 transaction, and T2 transaction also. Right? Now you observe I9 and I2, and T23 is requested. This is the item name, item 9 and I912. Sorry, item 912 is requested for by the transaction T23. I4 is requested by transaction T1 and T23. I44 is requested by transaction T8. Now you observe the colors. Now I7 is requested by T23. T23 made is dark. That means the request was granted. No other transaction is requesting for the item 7. Now you observe item 23. Item 23 is requested by T1, T8, then T2. These are all in queue. But you observe T1 dark blue, T8 is also dark blue, T2 is light blue. T1, T2 are dark blue means the requests are granted. T2 means light blue, means it is pending or waiting. You may be thinking how these two granted, because both may be shared locks. Granting is possible. T2 may be requesting exclusive locks, that's why it kept in waiting. If it is also shared lock, it might be granted. Right? So 912 item, only single transaction granted. And I4, T1 granted, T23 waiting state. For example, if any completed, let us assume that T8 completed, then it will be removed, that's all. Like that, the transaction table is going to be maintained as just like a hash table, depending upon the items for which the transactions are requesting. Those items only going to be considered for maintaining the status. The transaction aborts, all waiting or a granted request of the respective transactions are automatically deleted. Any transaction was aborted, and when the lock manager keep a list of locks held by each transaction, so that the transaction or lock implementation will be very efficient. It will maintain separate tables which transactions are maintaining, which locks actually. So that what happens when any other transaction is requesting for a particular data item also, then it will check whether transaction released or also. So that it will be implemented effectively. This lock manager will take care of the implementation of locks, granting of the locks, or releasing of the locks by the transaction, or properly keeps the track of all these transactions, requests, etc., so that the respective transactions are going to be served efficiently in the concurrent environment. Fine. But always the data item need not be a single data item. It will be sometimes composite also. That means it is divided further into sub data items also. Data item or any data object can be divided into further sub objects also. Then in such cases, what type of locks must be implemented? What is the compatibility of the implementation of locks on original data items to the sub data items? These things are going to be addressed by considering this multiple granularity. This multiple granularity means allow the data items to be of various sizes and define in a hierarchy of the data granularities, where the small granularities are nested within the larger one. Granularity means you just think about that generalization or a specializations concept like that, or a composite data items are further subdivided into subdata items. Subdata items are further subdivided into like that. It is a hierarchical structure. Generally, it is represented as graphically as a tree, but it is not a tree locking protocol. Observe that it can be represented. I'll show how it can be represented. When a transaction locks a node in the tree explicitly, it explicit locks all the nodes dissidents in the same node. So if a node is having any lock, then all its dissidents will also have the same mode of the locks. This granularity of locking means here level in the tree where the locking is going to be done will be desired. It will be having fine granularity or it will be coarse granularity. Fine granularity means here a lower in the tree structure. High concurrency, high locking overhead will be there. In case of coarse granularity, it is higher in the tree structure. So low locking overhead, but concurrency is also low level. So what is multiple granularity actually? A lock table consists of unit of data defines its granularity. Granularity coarse means the higher level, that is the entire database can be considered. Or it can be fine, that is at lower level, tuple level, attribute level also sometimes, relation level. The data item granularity significantly affects the concurrency control performance automatically. Why? Because at higher level, if you are putting exclusive means all its sub items can be already held, no, so no other transaction can access the entire structure actually. So the data item granularity significantly affects our concurrency control performance. That is, the degree of the concurrency is low if the granularity is at coarse. That means at higher level we are imposing the locks, the concurrency is going to be low here. And high concurrency will be there for fine granular. Lower level if you are including, then automatically next higher levels can be properly included actually. I'll give an example of the granularity. A field or a database record, that is a tuple or a relation, and a disk block or entire file or entire database. A tree structure was shown, you observe. This is the higher granularity, that is this database. This is at higher granularity, that is coarse granularity, and all these are fine further divided. You observe database is there, and database is having two areas, A1 and A2. Areas are further divided further as a files, FA, FB. Here A2 is having only one subfile FC. Each file will have records. Let us assume that this is the coarse, this is the finer. That means this is a hierarchical arrangement of our data, entire hierarchy of the entire database. Lower levels are areas, further lower files, further lower level or records. It may be further sub-considered. Sub items means attributes can be considered further. So when we are using such type of tree structure, if any lock was, for example here exclusive lock. Exclusive locks was held by some transaction or the entire database. Then what about the other transactions? Because a held on database means all its subcomponents also will have the same exclusive. Till that particular transaction releases databases, no other transaction at all enter into the process. That means at the coarse level, if the transaction locks are made, then all its dissidents will acquire, no? So in such cases, the concurrency will be low. That is, simultaneous transaction execution factor is going to be less. But at a finer level, the locks are given, finer granularity is there. Then the locks are allocated. Next higher level, some other locks are going to be given or not. It depends upon the request as well as the served by the respective lock manager. In such cases, multiple transaction may execute. No, so that is concurrency level is going to be, or concurrency factor will be increased. That means at course level, higher level locking system, if you are using higher level, that means course level you are using, then automatically what happens? The concurrency control factor will be less. If logging system is at a final level you are using, then what happens? Our concurrency control will be more. So that's why, depending upon our requirement properly, depending upon the transactions as far as possible, the locking manager or logging manager will serve the logs or requests which are not in course level most of the time. But other way also these logs are going to be implemented. We will consider to manage such a hierarchy in a proper manner to avoid that. That is the low concurrency control factor, to avoid that. In addition to read-write logs, there are 3 additional locking modes will be there. We have read-write no. For read, shared lock will be there. For write, exclusive lock will be there. Right? To avoid this coarse and to finer granularity concepts, because of locking system, to avoid the low level of concurrency execution of the transaction, we will consider, that is lock manager will consider some additional locking modes. These locking modes are known as intention lock modes. These intention lock modes are related to the multiple granularity of the data objects only. What are these 3 additional? Intention shared, intention exclusive, intention shared and exclusive. Shared and intention exclusive. Intention shared IS, exclusive generally shared yes no, exclusive means yes. But in intention shared we will represent IS, intention exclusive means IX. Shared and intention exclusive means SAX. What is this intention shared? It indicates that a shared lock will be requested on some dissident nodes. Shared lock can be requested on some dissident nodes, even though there is no lock on higher level. Intention exclusive means that an exclusive lock will be requested on some dissident nodes, that is child nodes. Similarly, shared and intention exclusive means that current node is locked in shared mode, but exclusive locks will be requested on the some distant nodes. Right? Current node will be having shared lock, but its children, that is next sub items, may request for exclusive lock. These intention locks allow a higher level node to be locked in shared or exclusive mode without having to check all distinct nodes. So no need to worry about that. These are higher level are independent of consideration. And as we have 2 locks compatibility matrix, similarly we have compatibility matrix of this total 5 locks. Right? Intention shared, intention exclusive, shared exclusive, and shared intention exclusive. 5 total. You observe, whenever intention shared is requested, all other locks are going to be possible except exclusive for the dissidents. Intention exclusive is requested if it is already there. Intention shared, intention exclusive and are allowed, but shared exclusive and shared intention exclusive are not allowed. Based upon this table, the locks requested by these sub data items will be properly observed and request is going to be fulfilled as per this compatibility. So in multiple granularity locking system, a transaction Ti can lock a node Q using the 6 rules are there, using all these 6 rules. The first one, lock compatibility matrix must be observed. First it has to be checked. And the root of the tree must be locked first and may be locked in any mode. The first root must be locked and it can be in any mode. If any item Q must be locked, then its highest level, course level must be locked in any mode. A node Q can be locked by Ti in S, that is shared lock, or intention shared lock mode, only if the parent of the Q is currently locked by Ti in either of these two. Same transaction, remember. Either of intention exclusive or intention shared mode. That means if the parent is having intention exclusive or intention shared mode, then its descendant, that is its child, can request or can be locked by either shared or a intention shared. Third one, when we are having fourth one, a node Q can be locked by Ti in X, SIX or IX mode only if the parent of Q is currently locked by Ti in either intention exclusive or shared intention exclusive. So whenever Q is requesting for a lock, depending upon its parent only, it is going to be served. And Ti can be lock a node only if it has not previously unlocked by any node. That is, Ti is a two-phase locking protocol. And Ti can be lock node Q only if none of the children of Q are currently locked by Ti. If it is a node parent node, its children should not get any locks by that time. So all these locks are acquired in the root to leaf order only, remember, whereas they are released in the leaf to root order. Root cannot release until its descendants completes their work. So that's why whenever a lock release comes, allocation will be root to leaf, but release of the locks is going to be considered leaf to root. Root cannot release the locks without considering the children's completion. Even it releases, it doesn't work at all. So like that, by using this multiple granularity, because most of the database system, this granularity will be there, but proper granularity we have to make proper in the sense that it should not be too depth, it should not be entire thing as a single component also, or a single object also. Granularity will be there or it has to be considered, but the level of granularity must be properly manageable. And whenever we are using any changes in our databases, those modifications are considered based upon versions. For example, when any softwares we are releasing, first version, second version, third version, any updates we are making in the software, next version is going to be released. Any product, not only software, any product version 1, version 2, version 3, like that we are going to. That means the upgradation of that particular product is going to be released by considering the recent versions. So multi-version scheme is applicable to our data items also. So the old versions of data items, to increase the concurrency control, we will maintain or we will store the old versions of the data items also sometimes. So if any multi-version of data items we are managing, then these versions are going to be given based upon the timestamp ordering. Timestamps are allocated actually. These multi-versions are going to be multi-version data items automatically increases concurrence because multiple versions of data items are available, So that's why if any request comes, the recent version or a old version, depending upon the requested requirement, can be served. So that's why concurrency will be increased, and it is implemented by using the techniques which already considered by us. That is, multi-versions can be implemented in two-phase locking protocol are timestamp based ordering. Each successful write results in the creation of a new version of the data item. New version means any write occurs, a new version is considered. Right? These versions are going to be labeled generally based upon the timestamps at which that particular write was worked out, no? Depending upon that, at which in the sense that not need not be clocked. It can be some units of time can be considered actually. When a read of queue operation is issued, select an appropriate version of queue based upon the timestamp of the transaction. So multiple versions are there, no? So which data has to be considered for this particular read statement? Depending upon the versions of queue, the respective read is going to be served. How to check it? Depending upon the timestamp. Return the value of the selected version only. Reads never have to wait as the appropriate version is returned immediately. No need to wait read versions. The respective wait is going to be released by us. In case of timestamp ordering, let us assume that queue has a sequence of versions Q1, Q2, etc. Qm. Each version of Qk contains 3 data fields. That is content, what is the data value of the queue, and write timestamp of queue, read timestamp of queue. So, write stamp of queue means here timestamp of the transaction that creates or return into a database, that is Qk. Read means the largest timestamp of the transaction that successfully read the version Qk. When a transaction creates, TI creates a new version Qk of Q, then that Qk's write stamp and read stamps are initialized with the transaction timestamp only. Initially, it will be transaction timestamp only. After that, it will be changed or updated depending upon the respective operations. Read timestamp of Qk is updated whenever a transaction Tj reads Qk. Any other transaction reads, its timestamp is going to be updated. And how it is going to be updated? The transaction timestamp, Tj timestamp is greater than read timestamp of Qk. Right? So that means the read only sharing, so then automatically depending upon the timestamp only, the respective read and write versions are going to be served actually. In multi-version timestamp schemes presented generally to ensure the serializability. That is, if the transaction Ti issues a read queue or write queue operation, let Qk denote the version of queue whose write timestamp is larger than the timestamp of the larger than or equal. Timestamp protocol similar to that only. Timestamp of the Tj, then it will be get served actually. This multi-version timestamp ordering depends upon the read and write transactions. If a transaction Ti issues a read queue, then the value returned is content of the version Qk. The transaction Ti issues a write queue and then condition will be checked. If the timestamp of Ti is less than read of Qk, then the transaction is going to be rolled back. Why? Because already the data was read whose timestamp is greater than the timestamp of the transaction means it has to be rolled back. Otherwise, if the timestamp of transaction Ti is equal to write timestamp of Q content, then it is going to be overwritten. That means always reads are going to be succeeded, but whenever write is going to be used, a lot of rules have to be checked. Coming to the two-phase locking protocol, there is a differentiation between read-only transactions and update transaction. In case of update transaction means exclusive locks are required, no? So read and write locks are required and hold all locks up to the end of the transaction. That is conservative, strict. That is update transactions follow the rigorous two-phase locking protocol. That is, each successful write results in the creation of a new version of the data item return, and each version of data item has a single timestamp whose value is obtained from the counters. That's why I told you it's not clock time, it is a counter, timestamp counter, which is incremented or decremented during the commit process. In case of read-only transactions are assigned the timestamp by reading the current value of the timestamp counter. So that counter will give the timestamp in case of two-phase locking protocol. In case of timestamp based locking protocol, the timestamps which allocated for the transaction, the same will be considered actually. In case of multi-version two-phase locking protocol also, this counter is going to be used depending upon the version of the data item. That is, TI sets timestamp on the version it has created, which is by incrementing the timestamp counter. TI increments the timestamp counter by 1 so that it can be considered as a next version. Read-only transaction starts after TI increments TS counter so that we'll see that values are updated by the TI. So the read-only transactions which are start before TI increments the TS counter will see that value before the updates the TI. In such cases, only serializable schedules are going to be produced. So that's why by using this multi-versions and multiple granularity, the concurrency control will be implemented most effectively. Thanks you. Thanks for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.